All right. Good morning, everyone. Uh, I thought we would start back in the argument of Aristarchus and see it all as a whole, as opposed to having it broken up over 2 weeks. So let's quickly go through what we've already talked about. His goal is quite amazing for 250 BC. He's going to find the sizes and the distances to both the sun and the moon. And this is even before his student Eratosthenes found the size of the Earth. He's after bigger game, the size and the distance of the sun and the moon. And what he's going to do is he's going to take natural phenomena. Ones that he takes is the angular size of the moon, how big it is in the sky as it appears in the sky from one side to if you sweep from one side to the moon to the other, what angle do you sweep across? He's going to take that measurement. He's going to take measurements from the solar eclipse, from the phases of the moon, and a lunar eclipse. The lunar eclipse is the most intricate and the most incredible what he does with the lunar eclipse, which ends his argument. But using these natural phenomena, he creates geometry out of these. And out of the series of geometries, series of proportions and other equations, he's able to do finally computations to get the sizes and the distances of the sun and moon. So let's see the structure of the argument. Okay, so here is the outline for the argument. He has 7 unknowns. The first 4 are the sizes and the distances to the sun and the moon. Okay, the capital D's will be the distances, and the little d's will be the diameters of the sun and the moon. Okay, he's going to introduce 3 more unknowns. He's going to introduce what he can call S. This is the length of the shadow of the Earth. Here's the sun, here's the Earth, here's the moon, and here's the shadow that the Earth creates from the sunlight. And of course, in the lunar eclipse, the moon moves into that shadow. So S is going to be the width of the shadow at the place of the moon. How far out the moon is, how wide is the shadow that the moon actually goes through. That's S. L is going to be the length of the shadow, okay, from the center of the Earth out to the length to the apex of the cone shadow that's created by the round Earth. That's L. And finally, D sub B, we're working with our little d's, will be the diameter of the Earth. Okay. This picture is one of the most famous pictures in all of science, but it is, as almost all astronomy pictures, are woefully not to scale. They're ridiculously not to scale, but they give the qualitative idea of what these values are. And luckily, if we're working with proportions, we can get away with these non-scaled pictures because the proportions will remain even though you scale it properly or not. So he has these 7 unknowns, and he's going to be able to derive from those phenomenon of the sky, eclipses and whatnot. He's going to be able to derive 6 equations. Now that sounds like he's one short, and he is. He has 7 unknowns, but 6 equations. What you can do with that algebraically is you can solve them all. You can solve those simultaneous equations for one of the unknowns. What do I mean by that? That is, he can find 6 of the values, 6 of the unknowns in terms of a 7. And given the algebra, you can pretty much choose which you want to use as that rock bottom unknown that you find all the other values in terms of. And the one that we're going to do here, the one that Aristarchus does, is the diameter of the Earth. Okay, the very last unknown. He's going to find the other 6 in terms of the diameter of the Earth. Okay, and for example, here's one right here. This one comes out of his analysis that the length L, the length of the shadow, turns out to be 114 times larger than the diameter of the Earth. He's going to find all the other values in terms of the diameter of the Earth, like this one. Well, that would be very disappointing if it ended there, but of course his student Eratosthenes comes along in his lifetime, and I think in his lifetime before he died, Eratosthenes goes ahead and independently independent of all this other analysis, tells us what the diameter of the Earth is, calculating the circumference of the Earth, and therefore calculating the diameter. So Aristarchus goes ahead and completes it and turns Aristarchus' mathematics into real numbers, numbers of miles, whatever miles were back in the day. So let us get started. We need to review three geometric ideas that we'll be using. One is similar triangles. When triangles have equal angles, their corresponding sides are in proportion. They have these sing-song proportions that we remember going back as far as middle school. We have the skinny isosceles triangle approximation. Very, very important. If you have a triangle like this in which the angle is very, very small, okay, and all of our triangles are ridiculously small. The angle here is, for example, typically is a half a degree. Okay, again, this picture is not to scale. Okay? What is this angle? This angle is more like 10 degrees or 15 degrees. Imagine an angle where this was a triangle where this was just a half a degree. There's a wonderful proportion that we can write, an approximate proportion. And given the height of the triangle and the base of the triangle and the angle of the vertex of the isosceles triangle, we have this approximation that the angle, the vertex angle, is to 360 as the base D is to 2 pi h. And where does this come from? It comes from not an approximation, but a theorem of Euclid that theta over 360 is equal to the entire arc AB of the circle. The curved line AB is to 2 pi r. Okay, so theta is to 360 as the arc is to the circumference 2 pi r. The reason why this approximation works so well is when this angle is very, very thin, the arc AB is virtually the same as the straight line distance D, and the height of the triangle is virtually the same as either of the two legs are. And that's why we can substitute D for the arc AB and H for the radius R. And so we have the very important skinny triangle approximation, which we'll be using a couple of times here in Aristarchus's argument. Okay, so there's just they're in symbols is what I just said in words. And the last little piece of geometry that Aristarchus is going to use is what I'm calling the skinny angle approximation. Again, if you have a very, very thin angle, okay, this angle here at C is very, very small. This picture is not to scale. And if you have an angle inside of it, in which the distance between the two vertexes are very short compared to the distance out from the vertexes out to the end where they meet. If this distance here from C to P is very small compared to the distance from C out to A, or equivalently P out to A, because C and P are very close together, then one can say, using the skinny triangle approximation, that the angle P is approximately equal to the angle C. And this makes sense. Okay? This can be justified mathematically. We're not going to bother to go ahead and do that. It's relatively easy to justify the skinny triangle approximation. Here it's a little bit more wonky, so we're not going to worry about it. Okay? But I think it is reasonable that if the distance from C to P is small compared to the distance from P out to A, that these two angles are approximately equal. Okay, we're ready to get started. The first one, the first phenomenon that Aristarchus is going to use is that the size in the sky of the sun and the moon are the same. It's shown every time we have a complete solar eclipse. If you happen to be lucky enough to be in that band of totality where the moon completely blocks the sun, virtually certainly for 250 BC, the moon exactly covers the sun. They have the same size in the sky. And because of that, we can draw this picture. And this picture shows that this triangle here of a height of the distance to the moon with the base of the size of the moon is in proportion, is similar to the larger triangle of the height of the distance to the sun is to the base, which is the size of the sun. Why are these two triangles similar? Because they're both isosceles triangles with the same vertex. The vertex angle is the same. We know that the base angles are equal. Therefore, they must be equal to each other because they have to add up to the vertex angle. Okay. I'm running through these geometric arguments very quickly for those of you who can follow them. If you can follow the details of the geometry, don't worry about it. Okay. This is not something you're going to make up if you haven't looked at geometry in a long, long time. But for those of you who are familiar with geometric arguments, you can see these arguments here are actually very, very simple. They're not simple if you haven't seen them in a long, long time. Okay. So these triangles are similar, and therefore the corresponding parts are proportional. And here's what they look like. The distance to the sun is to the distance to the moon as the size of the sun is to the size of the moon. Okay? And these are the sing-song proportions that you can make from corresponding parts of similar triangles. And this is where he's going to derive a number of his equations from these similar triangles. So we have our first equation. He now turns his attention to the actual size of the moon itself, which he measures to be 2 degrees. No one can figure out why he used such a bad number. The correct number is more like a half a degree, which he did know about and writes about in later writings, but he used 2 degrees in his writing and left it that way. And this is one of the sources of where the computations go wrong because of a bad measurement like this. In all cases, his geometry is perfect. Some of his measurements are not good, his fault, and some of his measurements are not good, not his fault. Just didn't have the technology to make them. But we'll use the good number of a half a degree, and here we have a perfect example of the skinny triangle approximation. If the distance that he measures, you measure this with a sextant, the sweep going from one side of the full moon to the other, measures this as a half a degree, then isn't it true that a half a degree is to 360 as the diameter of the moon is to 2 pi capital dm. This is the radius, right? This is the height, the distance to the moon. So isn't a half to 360 as the straight line distance, diameter of the moon is the entire circumference, 2 pi dm. And that's what we've written down. And he has his next equation. Okay. We can simply solve for that ratio. Okay. So dividing both sides by 2 pi, we find out that the ratio of the distance to the moon is to the diameter of the moon is about 114. Not a bad number at all, because that 1/2 is not a bad number. The modern value is more like 110. 114, 110, not bad. Okay. And from the previous proportion, we can also mix and match the different d's. And therefore, the distance to the sun is to the diameter of the sun is also that same 114.6. Let's go on to the next equation. This is a beautiful one. This is one of my favorites. He's looking at the phases of the moon, and he asked the question, when is the moon exactly at quarter moon? When do we see half of the moon lit? Okay. Here's the new moon, where it's not lit at all. It's dark to us. It's lit on the opposite side. Here would be the crescent moon here, okay, where the sun is illuminating this part. We only see this part, and so just this little part is illuminated to us. The rest of the illumination we don't see, so we get the crescent moon. Where is the quarter moon? When is the moon half lit? Okay. Here, approximately. We would get the Gibbons moon further back, and finally the full moon. So is there a geometric characteristic of exactly the quarter moon? And Aristarchus says, yes, you will get this exactly when the sunlight is just tangent to the orbit, the path of the moon. Okay. When this just kisses the path of the moon, not cutting into it in any way, look at what you get, guys. Here is the illumination of the moon. Okay, this is how much of the moon is illuminated by the sun, and this is the moon that we see. And how much, what is the overlap? Exactly the quarter of the moon. The moon looks to us like it is half lit and half dark. Exactly when the sunlight is just tangent to the path of the moon. And we know from Euclid that that is the case, therefore, that the radius line from the Earth up to that path would be at a right angle to that sunlight. That the radius line and the tangent line are always perpendicular to each other. Well, he can take a measurement of that. Okay? He can measure what's called the elongation of the moon. The elongation of any body is simply the angular distance from the sun to that body. He can take a measurement, very, very difficult measurement to make, but he's got a right triangle here. This is a right angle. If he, with this measurement, okay, look what he has here. He has, for this angle, he has the adjacent and he has the hypotenuse, okay, of a right triangle. And therefore, the cosine of this measured angle is the adjacent over the hypotenuse. And with that measurement, he takes it to be 87 degrees, and you can look up in his trig tables, which don't exist yet, but he can, by other means, find these ratios much more difficultly, turning the ratio upside down. So instead of having a number less than 1, we'll get a number greater than 1. We can write the 1 over the cosine, essentially, and we would get the ratio of the distances, the ratio of the sizes to be 19.1. This is a terrible number because 87 is a terrible number. Okay, the number actually, the modern number is more like 89.85. Are you kidding me? How do we measure the angle 89.85 and know it's not 90 degrees? Okay, what kind of instrument? We would need quite a sophisticated instrument. So none of the instruments that we're used to, compasses and rulers and things like that, and protractors, would possibly be able to make this distinction. Why is this angle so large? Because this is 250,000 miles. And this is 93 million miles. Imagine if this triangle were to scale. Imagine drawing a triangle where this is 1/4 of an inch and this is 93 inches. These two lines are almost parallel. Okay, they're not. Okay, there is some daylight, but for Aristarchus, he could only make an approximation like this. He did know that this was a bad approximation. He did know that, in fact, the number should be larger than 87, but he really had no way of knowing, so he left it at that. And he left it at the fact that the ratio of the sizes of the sun to the moon is the same as the ratio of the distances of the sun and the moon, and that is approximately 19. That the sun is 19 times larger than the moon in diameter, and it's 19 times further away. No, it's not 19, it's 400. Okay, that's because of the 87, not because of his geometry. The numbers are wrong because the computations he's doing are wrong, not because his geometric equations are wrong. It's because the numbers inside those equations are wrong. But yet, we have yet another equation as we go through building these 6. Let me stop here because this is such a nice one. Any question about this particular piece of geometry? Talking about the fact that we create a right angle when we get the quarter moon, just when the sunlight just touches the path of the moon, creating a right angle, and therefore we can use our simple trig functions for the right triangle to come up with this cosine equation. Any questions about this this here? This is called the dichotomy of the moon. And this measurement is still difficult. So we have much better ways of measuring now, finding the distance to the moon. Okay, so we go on to the last one. This is where we left off last week. This is the most beautiful of all, most intricate of all. One of the things involved here is he's going to measure time. He's going to make a deduction from measuring time. Here we have the lunar eclipse. We have the moon moving into the shadow of the earth, the sun. Sun, the earth, the moon is going to move into the shadow of the earth. And he asked the following question. He says, when the moon just starts to enter the shadow, let's measure how long it takes for the moon to be completely engulfed in the shadow. How long does it take when it just gets started and it finally disappears? Let's take that measurement. For simplification, guys, let's say it takes an hour. taking very, very simple numbers. Let's say it takes an hour for the moon to get engulfed in the shadow of the sun. Now let's measure how long it stays in the shadow. How long is it lost in the shadow? How long is the moon completely red, that beautiful red color that it takes on in the eclipse of the moon? How long does it take before it begins to emerge from the other side of the shadow? What Aristarchus found was that it also took an hour. That hour, which is not a real hour, but we're not using his numbers. He found it took the same amount of time to move through the shadow as it was to be engulfed in the shadow. What does that tell you? It tells you that the moon, the diameter of the moon is two shadows, because it'll be here, getting lost in the shadow, and then one more to move up to the edge. So this S, this little S, must be 2 times the, the diameter of the moon must be, I was saying it correctly, that the length S must be twice as long as the diameter of the moon. If it takes an hour to get lost in the moon and another hour to get across to begin to emerge, then there are 2 widths of the moon in that shadow. And that's what he measured. Again, these are not easy measurements to make back in his time, but he did, and this is the number that he does use, that this number S, the width of the shadow out at the moon, of the Earth's shadow, is 2 times the diameter of the moon. So he has another equation. The modern number is more like 2.82. Again, this is not a good number. And this number actually varies because of the elliptical orbit of both the Earth and the moon. This number will change with different eclipses, or even this number of 2.82 is more like an average number over many, many eclipses. And finally, we come to the last picture. I'm sorry, this is the next to last picture. Get our bearings here. Here is the sun and here is the Earth. We know that when we look from the Earth, we see the sun, it's a ½ degree in the sky. Again, this picture is ridiculously not to scale. Okay. And Aristarchus wants to know, how long is the shadow? What can we say about this shadow, which he's calling capital L? And the first thing he attacks is the apex angle that the cone of the shadow makes way out in space. This is way out beyond the moon. He wants to know, what is the angle of the cone of the shadow of the Earth cast by the sunlight? Such a question to ask. Think about that question. He's envisioning this enormous cone of darkness thrown out to space, and he wants to know the angle of the apex of the cone. And he wants to know the length of the cone. He knows the base of the cone. The base of the cone is the diameter of the Earth. Okay, here's the base of the cone here. He wants to know the other geometric properties of this cone of shadow. He wants to know its length, which he calls L, and he wants to know the apex angle theta. And here we use the skinny angle approximation. Aristarchus realized that this distance here is small. Even as long as the length may be, this distance is small compared to how far away the sun is. He realizes he can use the skinny angle approximation, that his distance L is very small compared to the distance out to the sun. And in fact, the distance out to the sun is 100 times larger than L. And so he's very much entitled to use the skinny angle approximation, and he calls the apex angle a half as well. This is the one place where he uses that approximation. And it's used to good effect. Why? Because he understands physically that the sun is very, very far away from the analysis he's already done. Okay, he's got 19 as a computed number, but he knows it's much, much larger than 19. And so he goes with the fact that this number is very, very large, and L, as long as it is, as big as that shadow is actually short compared to how far away the sun is. It's short because the sun is very far away and because the Earth is much smaller than the sun. And L is not going to be all that long compared the size and distance of the sun. So he makes this leap of intuition of a scientist to know this. Okay, we now come to getting close to that famous picture here. He's now going to tackle the actual length L. Now that he has theta out here, now that he has a half, he's ready to tackle L. But that's the skinny triangle approximation, guys. Isn't a half to 360 as the distance L? I'm sorry, let me say it again. A half is to 360 as the diameter of the Earth is to 2 pi L. That's the skinny triangle approximation. The angle is to the whole 360 as the straight line distance, diameter of the Earth, is to 2 pi L. And it's right here. That's what I just said. A half is to 360 as the diameter of the Earth is to 2 pi L. And we can go ahead and calculate L over D gets a number. Okay, 360 over pi gets a number, 114. And so L is 114 times larger than the diameter of the Earth. Yeah, the length of the shadow is very long. Okay, it is very long out in space. It's 114 times the distance of the Earth. And this is an example of what he's looking for. He's looking to get all of his unknowns like this, whereas all the unknowns should be multiples of D sub B. This one comes right out of the analysis of the skinny triangle approximation. And finally, okay, and to remind you, this is one of the most famous pictures in all of science. Okay, this is a picture out of his work. Okay, we're going to use it here. Okay, for the last of his proportions. He's interested in this triangle here. Okay, when you stand on the Earth and you look at the moon, okay, we have this cone. We know that this is a half a degree, that the angular size of the moon is a half. He has this triangle here, and he has this triangle here. We were just working with this bigger one. Now he's interested in not going all the way to the diameter of the Earth. He just wants to go to S. Yeah, he just wants to come here. He's got two triangles, this small triangle and this larger triangle here. They are similar because we know this is a half a degree. We've measured this, and from the skinny angle approximation, we know that this is also a half a degree. These are two isosceles triangles with the same vertex angle, and therefore their base angles are equal, and therefore these triangles are similar. This small triangle here is similar to this larger triangle here, and we have proportional sides. And what are those proportional sides? He can say, well, the diameter of the moon, that the distance of the moon, the height of this small triangle is to its base, diameter of the moon, is the height of this triangle, mentioned in a second, is to its base, which is S, proportional sides. The height is to the base, the height is to the base, as the height is to the base. But what is this height? This is nothing more than L minus the distance to the moon. The height of this triangle here is all of L minus the distance to the moon. All of L minus the distance of the moon. So the height is to the base as the height is to the base. The last of his sing-song proportional sides triangles. And here is just a little bit of algebra. We can substitute for S, the base, 2 times the diameter of the moon. We can substitute for L when we're ready, 114 times the diameter of the Earth. And let us take this. I'll take S and substitute this thing here. And again, just your math types follow a very simple algebra, right? Let's multiply up, bring the 2m up. The m's will cancel and we'll wind up with 2m. Let's bring this capital 2m over to make 3m, and L is simply 3 times dm. For you not math types, take my word for it. We just solved this little equation. If L is equal to 3 times dm, then dm is a third of L. but we know that L is 114 times the diameter of the Earth. And therefore, Aristarchus gets his first major result, that the distance to the Earth is 38 times, that's 114 divided by 3, and that the distance to the Earth, the distance to the moon is 38.2 times the diameter of the Earth. This is remarkable because the modern value is 30. Okay. That's pretty close, given the bad measurements that he's working with. The algebra is dependent upon the numbers. The function, the structure of the algebra is dependent upon geometry. And the geometry is perfect. And therefore, the algebraic equations are perfect. The numbers he puts into those equations are very, very faulty because of the measurements that he's using. So he gets 38.2. This is the first time, of course, in history that we have a number that talks about this, how far away the moon is compared to the size of the Earth. Again, I'll stop here. Any question about these two triangles, what he's doing to get the height is to the base as the height is to the base. The only little wonky part here is this height here is all of L minus the distance out to the moon. And that's where this funny term in the numerator comes from. The rest of it is just two similar triangles. Question?
Not a question, but a comment, Peter.
Yes.
I hadn't appreciated the extent to which approximation or close enough is fundamental to this sort of analysis.
Mike, if I can remind you that you were one time in your career an engineer, and you know how important approximations are in the world of engineering. It is the same here. Okay, he is actually doing mathematical engineering because he can't do the exact stuff. He can't do the pure math. So he puts on his engineering hat using these approximations. And he knows very much the way when you build something, you know that those approximate numbers that you're using for the specifications are good enough that the machine will work. He's doing the same thing here, that the numbers he gets out will be very good approximations to the numbers in the real world. Okay, this is exactly the analogy that engineers use all the time. Good point. All right, so that's it. He's got his 6 equations. He's ready to just go ahead and calculate all of these different values, the 4 that he's interested in terms of the diameter of the Earth. He finds, as the first one is, the distance out to the moon is 38.2 Earth diameters. The modern value is 30. He finds the diameter of the moon to be 1/3 of the diameter of the Earth. The modern value is a bit more than 1/4. Okay. His moon numbers are quite remarkable, given his bad measurements. The sun is woefully underestimated. The distance out to the sun is only 726 Earth diameters. It's really more than 11,000. And concomitantly, the diameter of the sun is only 19 times the diameter of the Earth, which is going to be just 6 Earth diameters. It's more like 109. So his results for the moon are truly nothing less than remarkable. This is a model for the world. Going forward, guys, this is what people turn to, what mathematicians and astronomers turn to. They turn to this work of Aristarchus to learn how it's done, because this is the first time it's done like this. This is the first time it's done on this kind of scale to tackle such an incredible project. And as I said, his underestimations of the sun have a very understandable reason given the measurements. Everything is in terms of the diameter of the Earth. He just has to wait for his student to come along to measure the diameter of the Earth independently, which he does to better than 5% for Aristarchus. So Aristarchus's legacy this is truly the first really great mathematical achievement in the world. Okay, there's great mathematics before this, Euclid, of course, but in terms of analyzing the world using mathematics, there's nothing quite like this. This is before Archimedes. Okay, this is 50 years, maybe 30 years before Archimedes, who's the one who invents mathematical physics. This is before all of this. All that he has is the geometry of Euclid, and he tackles this project. The enormous size of the sun was amazing. People did not realize how big the sun would be, at least 19 times bigger than the entire Earth. It's a staggering thing when you think about it, ancient peoples realizing that. And of course, Hipparchus and Ptolemy and all the other astronomers followed the models of Aristarchus in their research. And historians believe that this is where Aristarchus came up with the idea of the heliocentric system, okay? Once he realized that the sun was so much bigger physically than the Earth, okay? You know, you have no notion, you're just looking at points in the sky when you look at the planets. The only thing that has any size at all is the sun and the moon. Well, the moon is smaller than the Earth, and everyone knows the moon goes around the Earth. No one ever disputed that the moon goes around the Earth. The moon is the closest thing to the Earth. It blocks everything in its path. There's no question that the moon goes around the Earth. That was known soon, you know, before the Earth was round. Okay, but the sun being so large, Aristarchus says, really, the big sun is going around them, going around us? The universe is big, really big. Does it make more sense for the Earth to go around the large sun? And this is the speculation that many historians of science have of where Aristarchus came up with that idea. Okay, any questions before we close up our story of Aristarchus? I hope you enjoyed this, this exposition of his work, even if you didn't follow all the details. Certainly following the details of the algebra is completely unimportant. It's mechanics, okay? I hope you had an appreciation, everyone has an appreciation of how he takes these things that we see in the sky and turns them into geometry. That's the great takeaway. How much of that geometry you follow depends upon how much geometry you're familiar with. But the idea of turning these physical phenomena into geometric models and therefore making deductions, drawing deductions from these geometric models. Aristarchus is showing us how to do modern science. This is how it's done. This is how it's done today.
Peter, a question?
Yes.
I came in a little late, so if you've already covered this, I apologize. But Aristarchus, was he working on papyrus? I mean, what were the mechanics of how he could do this math and not lose track of it?
No, papyrus, right, was used by the, well, yes, he was in Egypt, in Alexandria. He may have used papyrus. I know the Greek world, the people, being a Greek, bringing down the Greek culture, they used parchment.
Mm-hmm.
Okay, so both materials were used, but they did have the ability to write and preserve scrolls. That's in the Great Museum of Alexandria, right? All those scrolls, and I think they were parchment scrolls, not
Okay.
papyrus.
Great.
Yeah.
Thank you.
Okay, so let us switch gears. I didn't wind up not using this because I didn't want to take the time. So let me bring up my other, because this we will use. We'll have a lot of fun with these animations. Apollonius and Aristarchus. Let me close down the other one that we don't need, Aristophanes. Okay, we've got our Mathematica that we want. And now let me open up the presentation. Okay. So building on the work of Aristophanes and Aristarchus, we come to two more mathematicians. Apollonius is actually a younger, almost contemporary of Aristophanes. Okay, if they had no overlap, very much Apollonius was born very, very soon after the time of Aristophanes. Not quite sure. I have a timeline coming in a minute. We can check that. So we're going to talk about the contributions of these two men, most importantly, Hipparchus. And if Hipparchus is not a name that you know, then I'm very happy to introduce to you one of the most important astronomers in all of science, in the history of astronomy. He is up there with all the greats, which I'll show you at the end of the presentation. We're getting close to Ptolemy's model, and so we have to begin to think about the planets, because the planets is the tough thing to explain. What we're going to try to do is show in Ptolemy's model, based upon the work of Apollonius and Hipparchus. All this comes to fruition in 100 AD by Ptolemy. What are the characteristics that we are after? We clearly cannot explain the whole Ptolemaic model. We're going to try to pick the most important characteristics that we see in the sky and see if Ptolemy's model, in fact, does explain that. If it is a description, his geometry is a description of what the sky watchers know to be true. And so we need to begin to accumulate those important descriptions. And here's the first one I want to point out. That in retrograde motion, which we've talked about, it turns out that the planets are brightest during retrograde motion. Very interesting. As you can see here, this is trying to depict the varying brightnesses of Mars as it goes through. And you can see that the planet is definitely brighter here than here and here. And this is what the picture is trying to detect. So let's chalk this one up. This is important. If you're going to build a model, Ptolemy, of the motion of the planets, you better make sure that when you come to retrograde, when the planets are in retrograde, they are at their brightest. That is, they are at their closest, because everyone equated brightness with closest. These are lights. The closer you are to a light, the brighter it is. So Ptolemy, if you're going to build a model, you better make sure that when all the planets are in retrograde, they better be closest to the Earth. Otherwise, your model is no good. Okay, so item one. So the planets are brightest during retrograde. All right, let's take a look at the work of Apollonius. How does Apollonius get this change in distance and therefore to get the change in brightness? By this device here, okay? We have the Earth in the center and we have our planet. And instead of having the planet just simply go around the Earth, he has a circle called the deferent, and he puts the planet on another circle called the epicycle. And so the epicycle circle is going to go around the deferent circle, and the planet is going to go around the epicycle. And this whole merry-go-round is something invented by Apollonius, brilliant geometer. And you can see right away that this solves the brightness problem, okay? Here, the planet is far away from the Earth, and so it's at its dimmest. And when it gets over to this place, it'll be at its closest and it'll be at its brightest. This is something that Eudoxus never addressed, right? Everything in Eudoxus were all concentric spheres. Eudoxus was only after the position in the sky. No, Apollonius and Hipparchus and Ptolemy are after more. They're not only just after the relative position in the sky, they also want to tackle brightness. Remember, Eudoxus tackled the retrograde, okay, most important, with that fancy hippodrome figure that he had moving around the ecliptic. This thing also will take care of the retrograde as well. But the first thing to see, the easiest thing to see, is that it certainly takes care of the brightness problem. Okay, the planet is sometimes closer and sometimes further away from the Earth, and so we will get a variation in brightness. Let's take a look at Apollonius's beautiful and brilliant construction of geometry. The first thing I want you to realize, guys, is that these circles that you're seeing are geometric figures from the top. What the Greeks envisioned were spheres. These are not circles. These are physical spheres. The Greeks had no idea that the planets could move in what we now call an orbit. That is just simply a path in space. They had no concept of this, okay? The idea of an orbit doesn't come to us until we have Kepler, okay, and Galileo. when they finally dropped these spheres. But here in the Greek world, we have the deferent sphere. It is a physical, complete sphere. And here is the epicycle sphere, where the center of the epicycle sphere is on the edge, the equator of the deferent sphere. And here we have the planet out at the edge of the epicycle sphere. And this is the motion that they're talking about. Okay, they're actually talking about a three-dimensional motion. Okay, and they can play games with these spheres. They can tilt these spheres a little bit, and therefore have the planets move sometimes above and sometimes below this plane here, which is just what Ptolemy is going to want to do, because sometimes Mars is a bit above the ecliptic and sometimes a bit above. We're not going to go into this level of detail. We just don't have the time. We don't have the mathematical wherewithal to look at this. But can you see qualitatively that when you're dealing with these three-dimensional spheres, you got even more of a play than you have just with the circles. We're going to work with the circles. The magic of Mathematica. Yeah. This is what we're going to work with. We're going to look from the top down. We're going to get this God's view, looking, here is the Earth here. We're looking down at the North Pole. And yes, what you do see is you see two circles. Okay, here is the deferent circle going around. Here's the epicycle circle being carried around the deferent, and here is our planet going around the epicycle. These are the pictures that we will work with exclusively. And in fact, these are the pictures that are in the Almagest in Ptolemy's work, okay? Realizing that we're working with the perspective of looking from the top down. But please try not to forget that these are physical, three-dimensional spheres that are creating this motion. Copernicus' title of his book is On the Revolution of the Heavenly Spheres. Copernicus continues to use this idea. We don't lose the idea of an independent motion of a planet without this kind of physical support until after Copernicus. Copernicus also needs this physical support to move his planets around. Copernicus simply puts the sun in the center of the deference and puts the Earth out as what he calls a mere planet. It is just another mere planet with its own deferent and epicycle. Okay, let us look at Apollonius's beautiful. Here is an example of the motion that we'll be looking at just in circles, looking from the top down. And so here we have a planet, and it is very bright because it's close, and it gets dimmer and dimmer, and here it's at its dimmest. And then it gets brighter and brighter and brighter, and then it's at its brightest, etc., etc. And it's a very pretty path. And this is the path of Venus going around the Earth. This is exactly what Venus looks like going around us. This very beautiful symmetric pattern. Okay? Notice Copernicus's model is much easier, with everyone simply going around the sun with simple circles. But if you want to take the Earth as the center, this is what you've got. And Apollonius gives it to us. Apollonius gives us this path. Okay. So it certainly solves the brightness problem. Let us take a look at the retrograde problem. It brilliantly solves the retrograde problem. What is retrograde after all? Here's the Earth. Here's our deferent circle. Here's our very, very big epicycle circle. Yes, no reason why you can't have a bigger epicycle than deferent. No, these things can be anything you want. This thing can go around as fast as you like. The planet can go around the epicycle as fast as you like. You have all kinds of levers and buttons to pick here in Ptolemy's model. Oh, you got lots of degrees of freedom. But after all, what is retrograde? Retrograde is when we see from the background stars. Okay, here's my background stars. When you see the line of sight from the Earth to the planet, okay, the planet seems to move around the background stars, and every once in a while it goes backwards a little bit and then continues going forward. Apollonius solves this problem. Let's take a look. So here we have a very different kind of path. because the epicycle is so much bigger than the deferent for Mars. This, by the way, is Ptolemy's model for Mars. Okay, the path is simpler, like this, much simpler than the Venus path. Okay? And guess where take a wild guess, guys, where the retrograde is going to happen, where the single retrograde per cycle is going to happen. Take a wild guess. Here's the line of sight. Look when we go into that loop. There it is. There's the retrograde. Here we're getting dimmer and dimmer and dimmer, dimmest. We're getting brighter and brighter. And at the brightest, we are in retrograde. Yes, yes. Apollonius gives the astronomers just what they need. We have retrograde, brightest at the same time. Okay, it's the easiest to see with Mars. All the other planets follow the same. Even that complex pattern of Venus has the same property, that it goes into retrograde in that inner loops there for the same reason. Okay? So Apollonius gives us this very, very powerful device to solve two of our great characteristics, that it does have retrograde. This does give the appearance of retrograde motion against the background stars, and that retrograde happens when the planet is closest to us. Okay, thank you very much, Apollonius. We will take great use of this. Question before I go on. I hope you're impressed with this very beautiful geometry. We're not going to do any proportions here right now. We're just going to show some pretty pictures. All right. Okay, let's go now. What is Hipparchus going to do with this device that Apollonius hands him? Before we leave Apollonius, though, Apollonius is famous for two things. First of all, giving us the deferent epicycle mechanism for the astronomers. He's more famous and more important in the scientific revolution. He's one of the three great mathematicians, three great geometers of antiquity: Euclid, Archimedes, and Apollonius, in that order. Apollonius is a younger contemporary of Archimedes. And his great work was on the conic sections, the parabola, the ellipse, and the hyperbola. He pretty much wrote the book on the mathematical properties of those curves. What the great irony is, of course, is that those are exactly the curves that the scientists of the scientific revolution needed to analyze the work that they were most interested in. Turns out that the motion of the planets, as we know, are ellipses going around the sun. And the whole notion of free fall, the motion of projectiles, the motion of inertial motion, and understanding moving into the laws of motion of Newton, the work of Galileo, is all based upon the work of the parabola. Galileo was the first one to prove that a natural motion has a mathematical thing like this. He showed that the projectile moves in a parabola. So these were the paths, these were the curves of the scientific revolution that Apollonius gave us 2,000 years ago. Okay? But the Greeks made no use of this. This was done as pure mathematics. There's no applications for these curves in Apollonius's time. Okay? Archimedes went ahead and proved more properties of these curves. Okay, and he used them in his geometry, the law of the lever, but nothing like these kind of things, the motions of planets, the paths of planets. We can actually use the word orbit now. Okay, these things were not, they were there, available. Apollonius made them available, but because the deferent epicycle mechanism was so powerful and so flexible that it really gave them what they needed to build their models. We'll see. The models that we'll build are all based upon the deferent epicycle kind of geometry, and didn't have to think about these other more advanced curves. No one asked the question, gee, maybe the sun goes around the earth in an ellipse. No, that was against Plato. What's with the hell? It's all circular motion. Everything is circles with the earth in the center, and everything is going around in constant speeds. Okay, no ellipses. These are mathematicians' toys. They have nothing to do with the real world of astronomy, nothing to do with the world of perfect forms, of the motion of the ether. Those are all perpetual, cyclical, circular motions. Can't break from that. And it never was. It never was. Okay. Copernicus never broke from that. He never broke from that. He never moved away from his circles. Spoiler alert, Galileo never broke from that. Galileo never broke from the circles, even though his contemporary was Kepler, who showed the world that they were ellipses. Galileo couldn't give it up. Okay? That's how powerful this idea of the perfect forms, that the planets, that the heavens had to move in perfect cyclical circles. It held the imagination of the Western world for over 2,000 years. I want to talk about the influence of Plato. Never mind his philosophy, just his cosmology, which is completely wrong, held sway for 2,000 years. Okay, so here's that timeline that I promised you. All these names you know. We've gone through all these names. I think one you don't know, the Merton cycle. We didn't talk about that, but everybody else is there. All of our friends are there. I think very, very nice. You can see, kind of get an idea from Thales around 600 all the way through. I added Euclid here. This is where Euclid belongs, around 300 BC. We have the great Archimedes. We're not going to have time, guys, to do Archimedes, unfortunately. We're just not going to have the time. He's not central to our story in terms of the models of the planets and the sun. He's central for everything else, but not for this. So we won't have time to do Archimedes. Here's Apollonius, a younger contemporary of Archimedes, and finally Hipparchus is way down here, about 150 BC. But all these names here are all before in the BC era. Okay, we come to Hipparchus. We've got about 15 minutes. I don't think we can finish Hipparchus, but we can get a good start. Hipparchus is the most important astronomer of the ancient world. He worked in Rhodes. He built his observatory up in Rhodes. He was not a creature of Athens or Alexandria. Although he probably was trained in Alexandria. I'm sorry, trained in Alexandria. Okay, he used star and planet positions going all the way back to the Babylonians. Okay, he used anything that he thought was reliable. So he built these incredible star charts based upon his observations of the Greek astronomers that he had records for. And going back to what Jim was asking about how do you keep these records? Well, they were all in the museum, right, of Alexandria that he had access to, and the Babylonian records were being transcribed and held in the great library of Alexandria. The librarian, by the way, at the time was Eratosthenes, and he also, with nothing else to do, he developed plane and spherical trigonometry. Yes, the mathematicians and the astronomers are the same people here, okay? Yeah, he invented plane and spherical trigonometry. He also invented the first modern coordinate system. How do you identify places in the sky, okay? He basically used the idea of longitude and latitude coming from Eratosthenes, okay? He has the equator of the Earth thrown out to the stars, thrown out to the celestial sphere. So this is the celestial equator. And here's the axis of the Earth. So here's the celestial equator. And then we have the ecliptic, which we know was at an angle, going around also the various constellations of the zodiac. They're at an angle. Here's the first day of summer. Here's the first day of winter. Here's spring, fall, etc., etc. Here's the axis of that circle. Hipparchus is the first one to say, well, let's go ahead and measure from a certain point. And he took the spring equinox as that point. This is the Greenwich. This is the London of our longitude. Okay, so he takes the spring equinox, the place where the sun crosses the celestial equator. He takes that as 0. and he measures across longitude. In astronomy, it's called the right ascension. And then from that place, he goes straight up to the star, and going straight up, that's the latitude. That's called declination. And these are the coordinates of the celestial sphere, okay, done by Hipparchus. We still use it today. He had another one going from that same place, where the sun crosses the celestial equator, the first day of spring. You can also move along the ecliptic. You can see how far along you have to go, the so-called celestial latitude, to get directly underneath the star, and then you go straight up from the ecliptic to the celestial latitude and longitude. So there are two different mechanisms, two different coordinate systems you can use depending upon what you use as your equator of the celestial sphere. You can use the equator, which is the projection of the Earth's equator, or you can use the natural equator given by the world, given by the sun, the path of the sun around the celestial sphere. So we have Hipparchus to have that, and this, of course, allows his records that we have, particularly Ptolemy, using these records to great effect, because we have very, very definite numbers to use and understandable where the objects in the sky are based upon Hipparchus's coordinates. We're not finished with Hipparchus. The other thing that he did was he gave us the system of magnitudes, of brightness of the stars that we use today. You know, we have first magnitude stars and second magnitude stars, and down to, I think, the sixth magnitude is the dimmest we can see with our naked eye. Not our eyes, guys. We're beyond the pale. Our grandchildren's eyes can see stars down to the sixth magnitude. We're lucky maybe to get a fourth, and in the city we're lucky to get a first magnitude. All the other stars are washed out. And this magnitude system is still used today, very much modernized, of course, with more sophisticated mathematics, but the basic idea is the same. Okay? And here is the brightest star in the sky here, using the modern system, has a magnitude of minus 1.46. The standard would be Arcturus or Vega, being called a magnitude of 0. So, for example, Spica would have a magnitude of 1, first magnitude stars. Here's the North Star, a little bit dimmer, has a magnitude of 2. Here are the brightest stars in our sky. And the brightest star, Sirius, is so bright, it actually is brighter than Vega, which has a magnitude of 0. And so it actually is given a negative magnitude. You can imagine the magnitude of the sun. If the magnitude of Sirius is a minus 1.46. Okay? These are not Hipparchus's numbers, guys. These are the modern numbers. Okay? And the winter sky is really so nice. I hope you guys get a chance to take a look at the winter sky when it comes, because it is filled with so many of the bright stars. If you want to see bright stars, it is the winter sky that has so many. And it's the winter time, the sky is clear and crisp and cold, where we are, and we get a beautiful, clear sky, in our rural parts of the country. And so you can see, if you just look at these names, Capella and Aldebaran and Betelgeuse and Rigel, they're all here. They're all in this list of the brightest stars in the sky. They're all together in the winter sky to be looked at, centered, of course, in Orion. So I invite you to do that. But not only the stars have a brightness to them, the planets do as well. Okay, and here is again, Hipparchus used the same system that he had, which is much updated with these new numbers for the brightness of the planets. And you won't be surprised that the sun is a magnitude of minus 27. Okay, it's off the charts. The full moon is the next brightest thing in the sky, minus 13. The quarter moon is brighter than any of the stars. But now we get to what's interesting. Venus has a brightness of minus 4.9. The brightest star in the sky is Sirius at minus 1.6. Okay. How do we read these numbers? These numbers are based upon Vega. Vega being a magnitude of 0, calling it a brightness of 1. What this means is minus 4.9 means that Venus at its brightness is 90 times brighter than Vega. That's what this 90 means. That the quarter moon is 250 times brighter than Vega. And the sun is 63 billion times brighter than light. Clearly, these are not linear relationships. Okay, this is a log relationship. This is very wonky. We don't need to worry about this. Venus is the brightest star in the sky. Venus at its dimmest is brighter than any other star in the sky. Venus is always the brightest star in the sky. That's why when you first see Venus, it is the first star that you see at night. It is the first star that comes out. Okay, when everything else is still washed out by the twilight of the sun, Venus comes out first because it is so gosh darn bright. When you first of all see Venus in its full brightness at night, you think it's a plane. You think it's an airplane until you realize this is not moving. This bright light is not moving. Yeah, that's Venus. You are now looking at Venus when you see a star that looks like a plane when you first look at it quickly. Jupiter is very bright. When Jupiter is at its brightest, it is the next brightest star in the sky. And very interesting, when Mars is at its brightest, it is then the next brightest star. Mars and Jupiter at their brightest are pretty much the same brightness to our eye. They're both about 15 times brighter than Vega. What's interesting is that Jupiter at its dimmest is also very, very bright. Look at Mars at its dimmest. Mars is incredibly dim. The variation of the brightness of Mars is very, very dramatic. Right? We know that Mars is the most elliptical of the big planets. Mercury is a special case. It is more elliptical, but Mercury is almost always lost in the glare of the sun. Okay, Mars has a tremendous swing in brightness. Therefore, it has a tremendous swing in distance. That's why that epicycle had to be so big to create that enormous swing. Sometimes Mars is very, very close to us. When Mars is close to us, it is our closest neighbor. It's closer than Venus on the other side. And when Mars is far away, it's very far away. Okay, it becomes very, very dim. So this is very interesting. Mars at its maximum and Mars at its minimum. When Mars is at its brightest, it is 15 times brighter than Vega. At its dimmest, it is 15 times dimmer than Vega. Okay. And by the way, so much for the North Star being the brightest star in the sky. Please don't pass along that craziness. Okay, Polaris is a two magnitude star. It is 6 times dimmer than Vega, and many, many times dimmer than Sirius, the brightest star in the sky. So, again, as we look towards Ptolemy's model, these are the kind of things that we need to worry about, these changes of dimness. And Mars is very, very dramatic, okay? So Ptolemy, you better get a very dramatic distance change in Mars or we're going to be suspect of your model. Not to get too wonky, but we'll finish here with the precession of the equinox, which is another discovery of Hipparchus. Hipparchus was looking at his tables and the tables of the other Greeks before him and the Babylonians before them, and he noticed a strange thing. He noticed that the position of the sun, when it crossed the celestial equator, that is what constellation of the zodiac was behind the sun on the first day of spring, it wasn't the same as his constellation on his first day of spring. It seems to have swung from here, moving along from the past records. This was very strange. Hipparchus had the leap of insight that this place, again, on the celestial sphere, of where the sun crosses the celestial equator, must swing back and forth on the celestial sphere. It's sometimes in front of some constellation of the zodiac and sometimes on others. And he calculated the cycle of swing back and forth to be 36,000 years. Clearly, this was a leap. This was a approximation, an interpolation of the limited data that he did have. Well, the actual number turns out to be 26,000 years. And right now, this is where the sun is. The sun is right here at the edge of between Pisces and Aquarius. And in fact, because of this precession of the equinox, the sun, as it moves on the first day of spring, is moving into Aquarius. And this is where we get the Hair song from the musical, The Age of Aquarius. We're coming into the age of Aquarius when the sun will be in Aquarius on the first day of spring. And at one time, it was already back here in Aries. And still, the astrologers still call the first day of spring the first point of Aries. They don't seem to want to update their records. But this phenomenon was discovered by Hipparchus, and the only explanation he had was it must have been that the whole celestial sphere was wobbling very slowly back and forth. And because of the wobble of the celestial sphere around the Earth, the fixed Earth, this would change where the sun seemed to be crossing the celestial equator. This is a very good explanation geometrically, but not the correct one. In fact, it is the Earth that is wobbling, and this explanation was not done until Newton and his law of gravity. It is the Earth that is wobbling back and forth like a top, and the axis of the spinning Earth is actually wobbling like a slowing down top. And because the Earth is wobbling back and forth, it looks to us like the whole celestial sphere is wobbling back and forth. And that's why we get this swing back and forth of the precession or the motion of the equinox. That is the place where the sun is in the sky on the first day of spring. I mention this because it does seem kind of wonky, but it is one of the most important discoveries, made, and something that has to be explained if you want to build models. We're not going to go through an explanation of this, the Ptolemy's explanation of this. But I wanted to point out, and we'll end here, that during this analysis, looking back in the records, he wanted to go ahead and calculate as accurately as possible the year. How long does it take to get from the first day of spring to the first day of spring? We know we're in the world of the mathematician, of the scientists. We've left the philosophers so far behind, guys, when Hipparchus tells us that the year is 365 days, 5 hours, 55 minutes, and 12 seconds. Yeah, that's 6.5 minutes too long. Okay, we are in the world here of mathematicians, of people who take measurements. We are way away from the speculators of the astronomers. And this is the great tradition that we still live in today. And I think this will be a good place to stop. We'll pick it up here with the device of the eccentric. We certainly want to get through this presentation, guys, and move on to Ptolemy and go through Ptolemy's model and see how well he does. Let's take a look at his model, look at his cosmology, and see how does he get the characteristics that we want to point out. We've already pointed out a couple, brightnesses and retrograde and things like that. We've got a few more things to point out. Let's see how well Ptolemy does. I want to take the time to do this. We may not get to or finish, certainly, the last presentation on the Middle Ages. That's okay. We'll start there in the spring. Okay, when we begin the scientific revolution, we'll start there in the spring. I think it's important that we finish Ptolemy, and we have 2 more classes to finish Hipparchus and then the work of Ptolemy. And the work of Ptolemy, as Ptolemy will tell you in his writings, are completely built upon the work of Hipparchus. Okay, so we'll call it a day. Any questions or comments before we go? Questions or comments? Okay, so we did a lot of geometry. We have a bit more to do next time. I hope you're enjoying the geometry, because this really is the meat of what I'm trying to show you. I'm trying to show you not just the ideas, but some of the actual mathematics behind this. And I hope I'm giving it in a level that can be appreciated by people of different mathematical familiarities. All right, guys, if there are no questions, we'll stop the class and call it a day.